Thank you very much, Silvestro, for the introduction and the NCCR Robotics to give me the opportunity to share what we are doing at the NeuroEngineering Lab here at ETH. And today I want to give you just an overview and present you some results of our studies with people with leg amputation, and in particular with the use of electrical stimulation to provide sensory feedback to this type of patients, presenting exactly so wearable robotics for amputees with the focus on the neural integration and the neural connection of the prosthesis and so the bionic limbs with the nervous system. So what we want to do is connect men and machines to improve the quality of life of this type of patient. To do so, it's very important to study and to understand very well what is happening at the natural level, so in healthy subjects, in the healthy somatosensory system, and then try to translate the results and the processing and everything and implement these outcomes in the robotic devices in order to interface well these two systems. So I want to start with present something about and explain about our sense of touch. As you can see here, we use our hands to do tasks of everyday life continuously, and we interact with objects, regulating the force and interact in a certain way with all these objects and to accomplish these simple actions that for us are simple, but of course in the moment that you want to reproduce or replace this function with a robotic device, this can be really challenging. In particular, if you speak about touch, we can also consider that when the moment that we interact with objects, we use our hand in a very different way, and we touch the object in a different way to extract the feature, the important feature for us. For example, for texture, we move the hand on the surface of the object to understand the stiffness of the object. We squeeze the object, and in this way, in real time, we control the force, we interpret the signal, and then we understand and we have a clear perception of the object that we are manipulating. Why? Because we have biological sensors in our skin. So our peripheral nervous system is innervating the skin and with different mechanoreceptors. So we have these biological sensors, the biological receptors that are there to convert mechanical stimuli from the environment in something understandable by the brain. So translate this in the language of the nervous system, that is, of course, is electricity, bioelectricity. So in this way, the mechanical stimulus is converted in spikes that then are interpreted at different level of the nervous system, putting together all the symphony of these mechanoreceptors, because we have different type of these receptors that are able to extract a particular feature, that are more sensible to particular features of the objects. And all this information are then traveling on the highway of the nervous systems that are the nerves, and this information arrive then to our brain that interpret this information to manipulate the objects. And then what happened in the moment that we exclude this information from the sensory motor integration? So to show you the importance of the sensation in the motor action, I want to present you a very famous experiment performed by Professor Johansson in Sweden, where the patient was asked, this is not a patient, is an healthy subject, that is asked to perform a quite easy task, so just light a match. In few seconds, this is possible, no problem at all. But in the moment that they anesthetize the thumb, the index and the middle finger, excluding this information of the biological sensors, a task like this become really, really difficult to do. As you can see here. So this is because vision is not suitable to extract and to replace touch and to extract tactile information from the environment. And even after training, this subject needs time to accomplish the task. And so this is a proof of how strong is the connection for the correct sensory motor integration and to control and do fine movements. Another example is considering the case of patients. So if I ask you what is wrong with this guy, what is the disease that is affecting this person, you probably refer to something related to the motor system. So something related to the muscles or to the control and at the level of the motor system. But in reality, the motor system of this patient is completely healthy. But this is a rare neuropathy where the tactile information and the proprioceptive information are missing. So the patient is not able to use only vision to perform a simple task like walking or grasp a cup of water. Again, as the case of the healthy subject anesthetized. Similar problems are affecting people with amputation. In the case of people with leg amputation, they are suffering high risk of falls, dangerous falls, and they have continuously to inspect the prosthesis while walking, because the residual tactile feedback, that is the stump socket interaction, is not enough to predict maybe something that is happening at the foot level. The lack of sensory feedback is also one of the causes of asymmetric walking, reduced mobility, and increased fatigue that create long-term medical problems in this type of patients. And finally, if you think to have a limb without sensations, you don't perceive this limb as part of your body. So you experience what is called low prosthesis integration and low prosthesis embodiment. And this has also an impact on the high rate of prosthesis abandonment. So what we are developing here in ETH and several research groups here in Switzerland and also in Europe are in general called somatosensory neuroprosthesis. So our prosthesis connected to the nervous system, in this case via peripheral nerves, that are able to restore a kind of sense of touch or somatosensory feedback that combines together touch and proprioception. Here in ETH, we are developing neuro-integrated bionic legs, so that are composed by sensoride insole with pressure reposition sensors that we can read in real time during walking. Then we transfer this information to a microcontroller, then drives the stimulation of the peripheral nerves of the patient, in this case, the tibial nerve, using intrafascicular electrodes. In this way, we can communicate and translate the information of the interaction of the leg with the environment, with the nervous system, and code this with electrical stimulation. And then the patient can use this information and interpret in real time this information and finally walk better. So together with several institutions, also with the lab of Sylvester, the PFL, in the last years, we work exactly to connect prosthetic legs for transfemoral amputees with the peripheral nervous system. In particular, using the electrodes developed by Professor Stieglitz in Germany, that is a time electrode, that is a polyamide-based stretchable electrode implanted transversally inside the nerve. So you can see the nerve, the cross-section of the nerves with all the fascicles, the fibers. And then we have these tiny electrical contacts called active sites that we can use to inject the current. In this way, we can communicate with the nervous system. In particular, thanks to the surgical approach in which we implant 4 electrodes with 14 electrodes, 14 active sites per electrode, we have a total of 56 active sites implanted in the tibial nerve. And then, as you can see here, we have a transcutaneous cable in this version, and then this cable is connected to the external neurostimulator. So our electrodes are very small, and as you can see here, this is a 3D reconstruction of the nerve implanted with our electrodes. So we have the electrode implanted particularly so inside the fascicles, very close to the sensory fibers that we want to stimulate. So we need a low level of current to elicit an activation in these fibers. And here you can see a video of the simulation of the stimulation inside the nerve. So after 1 week after implantation, we start to stimulate with these electrodes, collecting all the data related to the electrical evoked sensation, because of course, a priori, we cannot know the position of the electrode with respect to the fibers, and so we start to map this electrode from every active site, and then we collect the information about the sensation location, so where the sensation is perceived on the phantom foot or on the phantom leg, the sensation type, and the sensation threshold intensity, in order to calibrate and have a precise and optimized electrode parameters, stimulation parameters for this particular patient. So it's a kind of personalized map of the sensation. And here you can see some of the sensation elicited in the 3 participant transfemoral amputees implanted for 3 months with this technology. So what we showed in a paper published in 2019, that with these intrafascicular electrodes, we were able to elicit specific and selective sensation on the plantar part of the foot, different type of sensation, and also sensation on the lower leg that also is missing. And then we connected with the proprioceptive sensations. After this procedure of calibration, we started we implemented this artificial sensation, artificial touch and proprioception in the neuroprosthetic leg. As you can see here again, we have sensorized with this wearable system the prosthetic leg, placing sensors and a sensorized insole, and we have also a knee encoder for the knee flexion extension. Then during walking, we record the data during exactly the gait, and then thanks to our we call sensory neural encoding, we translate the information from the artificial information from the readouts of the sensors in the electrical stimulation. And this electrical stimulation evokes sensation directly referred on the phantom foot and on the phantom leg, thanks to our neural implant. So the first part is to test if the patient is able to perceive sensation directly on the foot. So as you can see here, the patient with the prosthesis, we have the sensors. Stanisha here is touching a different part of the foot. The patient is blindfolded, as is instructed to reply, and then the patient indicated on the rubber foot where the sensation was felt. So, and in this way, this is the first time after 9 years that this patient was able to perceive sensation on the foot. And as you can see, he can in real time understand the position and precisely report with high accuracy the location of this sensation. This is very important to prove that this sensation can be exploited and is really understandable for the patient.
I feel this one.
And here, for example, is the patient experience.
An examiner is touching rubber foot with the sensors, and I feel the same place I feel touching on my leg. When it's touching my tongue or heel or foot anywhere else, so I feel every time I feel where he is touching the rubber foot. It was very interesting, like my own leg. First time I feel my leg. I feel my.
After this calibration and this implementation in the real-time system, we evaluate a series of benefit or potential benefit of this technology in the patient and in the prosthetic use in particular. So starting from the mobility, what we observed was an improvement in mobility. So the patient walked in general faster in different scenarios with our device. It's very important for as really an indication of efficacy of the device. Then we prove also some benefit on the metabolic consumption. So the patient also reported to, so what we measure is the metabolic consumption during the walking phase outdoor. And we prove that the patient consumed less energy to perform this task. This is very important because this type of patients are suffering high risk of cardiovascular disease and heart failures. And finally, also something related to the phantom pain. So a lot of patients report to have painful sensation and uncomfortable sensation coming from the missing limb. This is called the phantom limb syndromes and phantom limb pain. And what we observe is, thanks to this reconnection and flow of deformation that is coming back to the patient, the pain disappeared in one patient. In another patient was reduced during the intervention. So after these results, we then also ask ourselves, what are the underlying mechanisms promoted by this restoration of sensory feedback that can explain some of the results that we observed with the patients. So in particular, we evaluate the sensory feedback restoration with our system compared with the conventional prosthesis with the feedback, so feedback and no feedback condition in two tasks of everyday life. So one is the overground walking, and the other one particularly challenging for people with the transfemoral amputation that are climbing the stairs. So we ask the patient to ascend the stairs and descend the stairs, and in this task we measured all the kinematics data, so thanks to the market and cameras, and also the dynamic data from the sensorized insole on both feet. The first result that we obtain is that the neurosensory feedback improve patient mobility in both tasks. So in both tasks, both one easy task and one more challenging task, both patients, in this case our data of 2 patients, improve their mobility, and so they walk faster. Then analyzing the sensory motor strategies, what we observe is that the sensory feedback activates novel motor strategies in this type of patients. In particular, we observe for the overground walking task and higher cadence, but not only higher cadence, but also higher stride length. This means, and is a clear sign of a more confident walking, and measuring also the stance time, we observe a reduction of the stance time in this case. So the take-home message is that the patient is walking in a more confident way, increasing both cadence and stride length in this type of tasks. Analyzing the data from the stairs, we observe a reduction in the stance time in the swing time. And this is interesting because the swing time, so the moment in which the prosthesis is on air, was reduced with sensory feedback. And because normally the patient is inspecting the prosthesis, look at the stair before placing the foot on the stair. So he needs time, to place the prosthetic leg on the stair and then transfer the weight. And so we reduce the time that the patient needs to understand the correct foot placement. Moreover, we also observe a reshaping in the kinematics, where the ankle elevation was improved and was increased when the sensory feedback was provided, indicating that this is in direction, a more physiological way, in a more physiological exactly way to do this type of task. Then looking at the way in which the patient really use the prosthesis, we observe that the underlying code of the neurostimulation that is exploited by the patient during the task in the overground walking was in general the temporal information of the activation of the sensors. So the fact that the patient received during this walking phase the information of the heel contact, the lateral side, so of the foot, and then the forefoot, give a temporal, correct temporal activation of the rolling phase on the ground of the prosthetic foot, and this is important to have a better temporal coding about walking. And for example, also we observe on the stairs that the foot placement of the stair was different in case of sensory feedback and no feedback, and the formation of which sensor is activated is important for the patient to understand the correct placement of the stair. So, for example, when the patient ascends, so climb the stair, is important to place the entire foot or at least two sensors activated in order to transfer in a secure way the weight of the patient on the prosthetic side before step on the stair. And on the other side, it's important to, on the descending phase, to roll the foot and flex the knee. So the patient was using the formation of the heel sensor and the lateral sensor to understand that the foot was placed in the correct way. A second important result that we also study is not only the mobility, so the functional improvement of this device and the health benefits, but also the cognitive integration. So as we know, the sense of touch is involved also in the embodiment and in the sense of ownership. So in the moment that we restore the sensory feedback, we observe in general an higher embodiment of the device. And I think also Julia will talk about more about the embodiment. And in this particular task, what we observe was a reduction of the perceived prosthesis weight when the patient was walking with the prosthetic device compared with without. In particular, we asked the patient to do a motor task, so walking 10 minutes with or without feedback. And after that, we asked the patient to judge the weight, which leg of the two legs was heavier, when applying different ankle weight on the healthy side. And this is important because in general, patients are referring to have to perceive an higher weight of the prosthesis, even if the prosthetic left weight less than a healthy limb. And what we observe is that in general, when the patient is walking with the feedback, we observe a 23% reduction of the excess weight compared to no feedback condition. And so this is what we think is due to the cognitive integration of the device. So in a task, in a dual task, we ask the patient to walk and count and also spell some words, some letter, and we measure the number of correct answer and together with the velocity. So the dual task, so we ask the patient to do two tasks at the same time. So this needs a certain mental distress, so to not have an higher cognitive load. And this is also a clear sign of the embodiment in the moment that you see that the patient is able to perform easily a dual task compared with the no feedback condition. So all these results and what we can conclude for that is in general that this neural integration promote novel sensory motor strategies that can guarantee an increase in mobility and also in tasks of everyday life. And there is in general improvement in the spatiotemporal parameters, so both dynamics and kinematics gait parameters in all the subjects. And this neural connection also guarantee a certain, an important reduction of the perceived weight in one of the patients where we test this hypothesis, thanks to the better cognitive integration of this device. Now, very fast, I want to just present something about the system that we use in Cyberthlon. So in our lab, we are developing also non-invasive solutions. So something that is important because a second surgery is not always what the patient wants to do. Secondly, it's very long to certify the class 3 medical device compared to class 2, for example, and also it's much more expensive. So to be more maybe effective, also for the to prove it some benefit also with a simpler device, but can be maybe adopted by the patient faster, we develop a similar solution using non-invasive stimulation. So as you can see here, we have a similar system, so with the sensor again, with the encoder, but instead of having the electrode implanted in the nurse, we placed surface skin electrodes, a belt of surface skin electrodes around the stump of the patient, creating a belt of electrode, completely non-invasive, that the patient can wear under the socket. And then we built a remapped sensory feedback based on electrocutaneous stimulation. So in particular, this feedback is a remapped feedback, as I said. So this means that the foot is remapped around the stump. So when the patient is touching the ground with the heel, we provide a sensation and vibration on the back side of the stump when the patient is going on the side, on the front. And this is a modulated stimulation, so the patient is able not only to understand the location of the interaction under the foot, but also the amount of weight that is putting on the prosthetic side. And we use this technology with the NeuroLegs team at Cyberthlon, that I think you know is this famous competition for people with disability technology, as a team NeuroLegs. And I want to present you our pilot at Cyberthlon, Stefan.
Mein Name ist Stefan Poth, ich bin Pilot am Cyberthlon für das Team von der NeuroLegs. 2013, also vor 7 Jahren, im April, bin ich an einem schönen Frühlingstag spontan auf meine Töpfe gestiegen, habe ein kleines Ausfährtchen gemacht mit meiner alten Harley. Und auf dem Rückweg bin ich dann leider von einem Auto übersehen worden, das mir den Vortritt genommen hat und die Zeiten reingefahren ist. Ich habe dann auf der Unfallstelle mein linkes Bein verloren, also inklusive Unterschenkel. Die Menschen mit Behinderung, also mit der körperlichen Behinderung, sind darauf angewiesen, dass Firmen, Leute, Forscher sich auseinandersetzen mit der Weiterentwicklung der Prothesen. Darum finde ich es persönlich super, dass auch eine ETH sich da einsetzt. Und darum ist es für mich auch ein Anliegen, dass ich selber einen Beitrag leisten kann und dort mitmachen und helfen, dass wir die Prothesen weiterentwickeln und verbessern in Zukunft.
And together with all the team, the NeuroLegs team, with all the engineers, neuroscientists, was a really really nice experience. Also to have the user-centered development. So because Stefan was really part of our team, giving advice to how to make this technology better, and this with incredible team. Then we participated in Cyberthlon 2019 and also 2020. And here, so you can see the task in Cyberthlon, what are required specific skills for the patient, for the lower leg category in particular. They asked to have a prosthesis that can provide support for the static balance, for the precision of movement, dynamic balance. So our task of everyday life, but are also related to some specific characteristic of the walking capability. Here you can see the performance in the finals, I think, of our device and Stefan. So he's wearing the NeuroLeg system that is fully portable. And for example, you can see here that this is like a precision task because you need to have a certain control of the hip. And also is a dual task because the patient is asked to carrying object while walking. This is another one as I think the most challenging. I also failed walking on this. And where the patient is asked to walk on this wooden beam while he's carrying these heavy objects. And so in this case, the sensory feedback can help, for example, to understand the correct position of the foot and the amount of force that you are placing on the leg. And then other tasks, like for example, stairs, that, as I said, are particularly challenging for these patients. And of course, during the stairs, for example, in the moment that the patient is carrying object, it's difficult to see the interaction and the foot placement on the stair.
Okay, now it's good.
Okay, and this is the patient experience again.
Zoom sometimes just.
If it's possible to get more feeling in your foot, then more security to walk, and I think the potential of this to improve daily life for people with leg prostheses. So it's had nothing to do with the superhuman, but it has something to do with getting back in a normal way.
So I'm happy to say that we won the silver medal in both competition. It was really the emotional moment for us, for Stefan, and we hope to do better in the 2024 edition. And just concluding, I want to mention that this non-invasive technology and sensory feedback restoration, we are thinking to exploit this type of technology in combination with exoskeletons. In one case, together with Professor Micera's lab, Professor Riner lab, we are working to combine the NeuroLeg system and neuromuscular electrical stimulation and the MyoSuite to improve the performance of these wearable devices. And in the other case, together with the relab here in ETH of Professor Gassert, we are also equipping the TenoExo with the sensory feedback system that stimulate the arms nerves, in this case, providing a non-invasive sensory feedback for people with a partial stroke or partial spinal cord injury. So I think this is a very interesting approach, and we are really interested to see the future use of these technologies and tests of these technologies with patients. So I want to thank you for the attention. Thanks to all the labs involved in all these projects, in particular the NeuroEngineering lab, because we are a group of friends that work all together, and they're working a lot. Greta, Andrea, and of course Stanisa, the PI of the lab. And so now I'm open for questions. Thank you very much.